of silence, because since the January 2019 meeting, the country of Ghana has gone into mourning over the loss of past President Jerry Rawlings, which occurred just last week on November 12th. And so I will take 5 seconds of silence. Okay, so we ask that the calling stick be passed from Dr. Dudu Aran to this virtual workshop. So if you can present it forward, thank you.
So from Ghana, I present the calling stick, which is for our virtual meeting. Thank you very much.
And then in your other hand, you also have the scroll which describes the, which would be describing the contents of the meeting. As I have read here, it is a advanced light source for Africa, pumping out scientific discoveries. Now, at the end of these proceedings, we will call it again to Rwanda. That will be at the end on Friday. In November 2021, it will be called again in Rwanda for the rescheduled AfLS 3 next year. The calling stick's final resting place will be the future AfLS facility, where it will still call people to its campus. With this portion of the ceremony done, I would like to call forth our first speaker of the session, Professor Simon Canal from the University of Johannesburg, and he will talk about the African Light Source Project.
Thank you very much, Tabitha. One moment while my screen shares. Do you all see my screen?
Yes.
Okay, well, thank you very much for attending the African Light Source 2020 virtual event. It's a wonderful occasion to have you all here. We were going to be in Rwanda at this very time, but due to the pandemic, we have resorted to a virtual event. I want to tell you a little bit about the proceedings as they will unfold. And I want to give you a sense that we feel in the steering committee of the African Light Source. We have been organizing towards the African Light Source for 2 decades. And for this meeting, we want to report 3 very, very important milestones. We will launch our International Advisory Committee. We will launch letters of support and a MOU series of them. And we will also launch the conceptual design report process. Also on my slide here, if you download the PDF version, you will see documents, and I think they are fantastic reading if you want to see a chronicle of the progress towards the African Light Source. You can also find a little bit more material than this on our website. So I give you a reminder there. If you go to that link, it's our website. If you would go to the About section, then you will see some documentation ranging from 2 pages to more. And the most recent addition there is a survey of geology in Africa with light sources. I'll also remind you of the conference website. And I'm going to move on to my slides now. I want to first introduce you to the Executive Committee of the African Light Source, which you will also find on the website. And they are all around the world, and strong leadership from Africa and also friends of Africa. We also remind ourselves why we are doing this, and these are the reasons here. You can look at them more deeply, but we are feeling very strongly that past events have shown us that it's actually very urgent for Africa to move forwards with a light source. You will hear that other light sources, of which there are 50, many of them are undergoing upgrades. And I want to say the upgrade is about 10,000 times figure of merit improvement. And so it really makes Africa realize that we need to be in this game. Also, the importance of innovation that has been highlighted, and the synchrotron is expected to be a font of this. So we go on. I want to quote a very good friend of the African Light Source, is the executive director of the Third World Academy of Sciences at the moment, and maybe he's in the audience. I have this slide from him. It is a Professor Romain Morenzi, and he emphasizes that we need a light source because to have a wealthy, advanced Africa, we should have at least 1 million scientists. Scaling to the rest of the world, it means we're still only 1/6 of the average of a highly developed country. So that is also something the light source is going to bring us. I'm very pleased that in a little while you will also hear from the Ghanaian minister, the honorable minister, because Ghana has dedicated itself to be a champion of the light source. And now I would just like to mention that the African Light Source is engaged in top-down and bottom-up activities. And you see examples. This is a very, very large conference, took place just over a year ago in Africa. Also, the AfLS is written into the Africa Union, as you see documented here, is a decision that has been taken by the Africa Union that it is something that should be promoted. Later on in this conference, the Friday program, you will see the letters of support and they will be highlighted. You will see our International Advisory Committee. I can't say more because I'm leaving everything for the actual launch, but this is a very, very important step. Then there's the conceptual design report. Also, again, I don't want to say too much more, but I want to emphasize that as we take the light source to governments, we will need this conceptual design report. You will see it's 5 volumes, and it will really bring gravitas. I fully believe that the conceptual design report, when it finishes next year, if things go according to plan, that will be the date from which we say the African Light Source was launched. That will be the date that we all know what we are talking about. I also want to say in these conference proceedings, you are going to see highlighted a lot of partners of the African Light Source. The African Light Source is like a broad umbrella for many partners, and they will speak in the session on Thursday. And I just mentioned X-Tech Lab, which is an initiative in Benin, but it is in fact a regional initiative pumping out ultimately hundreds of trained people per year, and also important on the roadmap. But there are many such initiatives and you are going to see them. Then you also will hear from 4 scientists, particularly on science. So we have chosen energy, materials, environment, paleo science, and bioscience. And these are various days in this conference. So just to say, why did we choose paleo science, etc.? Well, this is the footprint of paleo science in Africa. One of our functions is to audit the science done with light sources. And this is not an easy task, but I want to bring you a very positive message that there's a very large footprint developing of light sources in Africa. Here's bioscience, it's just the feeder facilities. And these are groups that are fully competent to lead in bioscience at a light source. And this example motivation, I just wanted to include, particularly draw your attention to the last line. There has been African contributions to vaccine development, even in the current pandemic, and it has been structural determinations where function can be inferred from structure. And this is a very important slide because it establishes that a very, very important route for targeted medical interventions is light sources. And I want to draw to your attention that during the pandemic, highest level lockdown, light sources beamline on structural biology was an essential service all the way around the world. And that is really what has driven the development towards the drugs that are going to save the world, that you will see in due course. Now, material science, there's also a footprint developing in Africa. So I just want to say, if any of you do not recognize your country in this footprint, then please let the African Light Source know, because it's really mostly word of mouth that allows us to do the audit at the moment. But you do see a tremendous footprint developing in Africa in those fields that I mentioned, paleo, materials, and bio. I just want to end to say to you, please, I really hope you enjoy the conference and that it fills you with the same excitement that we have, that there will be a light source in Africa, and that there is tremendous momentum, and it is a massive boost from the items I mentioned that we will give prominence to in this conference. And I also want to say, please put in your diaries the 3rd week of November 2021. We are shooting for that date, Kigali, Rwanda, and that is where the postponed AfLS3, which is moving from this time to exactly 1 year in the future. So with that, I conclude my very brief introduction and I hand back to the chair. Thank you.
Thank you, Professor Canal, for a very, very insightful opening. Looking at the chat window in case there are questions coming in, but I will ask if anyone would have any questions for Professor Canal. And I do see that you do have Professor Canal from Dr. Thandeka Moyo. You have a note that the National Institute for Communicable Diseases in South Africa should be added to the list. So I ask you to check the chat window. If there are no more questions, then I will ask Dr. Waynegate to begin to share his screen. And he will offer some opening remarks on behalf of the African Physical Society. If you have slides, you can share the screen. If you do not have slides, then it's good enough to just begin to speak. Professor Waynegate. So I see a portion of your slides. Are you having trouble sharing the full set?
Professor Waynegate, are you muted?
Oh, he needed to be made co-host for sharing.
Okay, I'm going to unmute him. I see he's muted.
And also we are unmuting you, Professor Waynegate. I heard you and saw you earlier just before the start of the meeting, so we should
Yeah,
Can't unmute him. He must unmute himself.
yeah, right. Yeah, I can't unmute him.
Now, if they're, okay, I see you were struggling for the opening of the slides. I now have you in the screen view. If you're having trouble with the slides, Professor Wenge, if you would like to deliver without the slides, that will also be fine.
You can also email me your slide if you like.
So now you can hear me?
We can hear you. We can certainly hear you. That's wonderful.
Okay, so
But we still have trouble
my
seeing your
picture on
full
the-
set of slides.
Okay, so I can talk?
Yes, we can hear you well, but we can't see your full set of slides.
Do you hear me?
Yes, we can hear you very well.
Okay, so what I want to say, okay, I am talking on behalf of African Physical Society. I want to make a small historical reminder, you know. The African Physical Society was the first African mathematical society. And it was led by past Professor Alote, who was a professor of physics in Ghana, a very well-known physicist. And after our different interaction with Professor Alote at ICTP, at different African laser, atomic, molecular, and optical science network, so it was decided to create an African Physical Society. And one of the first meetings was in South Africa during the International Year of Physics in 2005 in Cape Town at Itemba Lab. And during this meeting, it was decided that the launching of the African Physical Society will be in Senegal during a lab meeting. This meeting was supposed to be in 2007, but due to some circumstances, the meeting took place in 2009 in Dakar with the launching of the African Physical Society. This was the picture that I want to show with a council member of the society, but unfortunately I cannot show it, but it is here. Can you see it? No? You can see it?
Yes, we can see it now. Wonderful. Thank you.
Okay, so it's fine. So this is the first council of the African Physical Society. And as you see, in the middle here, this is Professor Alote, who passed away, I think, in 2000 and I think in 11 or something like that. He was a wonderful person who really tried to put African scientists together. He was everywhere where people want to unite to do science. And okay, so what we do when Professor Alote passed away in concordance with ICTP, we decided to make a meeting in Kigali in October 2018 in order to make a kind of revival of the African Physical Society. Because in Dakar, it was constituted such that there was a President Alote, I was a vice president. So during the Kigali meeting, we were able to set up an executive committee, having in mind that in Senegal there was a president, a first vice president, and also vice president all over Africa. In North Africa, for example, here we have one of the vice president from Tunisia. We have a vice president from Cameroon, and we have international representation. Joe Nimela from ICTP, Sekazi from the US, the ALC representative, and many other people, Malik Maza from South Africa, from Algeria, and so on, all over Africa, you know, from Cameroon again. So, and the spirit of Kigali is how to make such that African Physical Society will continue to bring African people together to do science, to do physics for the development of Africa. And as for that, I have to say that I would like to really thank ICTP for its support and all of our international partners who really want to help African physical society. After that, we have opportunity to work with African light source. And today, to me, this is a great day. Today is a great day because we are now able to put two African society together, working together, having a common event together for Africa, for African to understand that they have to work together. Right now, my friend Simon shows that there is only 169 per million scientists in Africa, when in Germany there is more than 7,000 and so on. So we have a long way to go, and to do that we need to be together. We need to work together, and this meeting of African Physical Society and African Light Source was scheduled in person for this year, but due to the COVID-19 pandemic, it was not possible. And this is why we are running it as a virtual meeting. But I hope that next year, there will be an in-person meeting of our two organizations. I call them, I used to say that we are twin organizations. And today also, we will be lucky to be joined by the African strategy for fundamental and applied physics. I think they will also have a talk. And this is really, for me, this is a great achievement, because it is once again, it is important to work together. This is my message that I want to say. And I think that before next November, the African Physical Society will try to set up all the organizational structure in order to try to be more sustainable financially, because this is also one of the main problems in Africa. You know, our different society, it is difficult for them to get financial support, but we have to say that today this meeting is thanks to the technical support of ICTP, and once again, I would like to thank ICTP and to thank all our partners. This is all I want to say. Thank you.
Well, thank you for that very, very wonderful opening describing the African Physical Society and emphasizing the importance of really having more scientists and having multiple organizations working together, and hopefully we can achieve all that we endeavor. Are there any questions for Professor Waynegate? And if so, you can type them into the chat box. We ask that you remain muted if you are asking a question. And we ask if there are moderators who can help with the
Yes, I've been trying to help with the muting.
So if there are no other questions, I will move on to introducing the next invited speaker. And it's my great pleasure to introduce Dr. Ketevi Asemagan, who will talk to us about the African strategy for fundamental physics and applications launch. And while he is preparing to share his screen, I just want to emphasize that Dr. Asemagan has led the African School on Fundamental Physics, and more recently, that version of the, alongside of the school, the African Conference on Fundamental Physics. For many years, I believe the school dates back to, I believe, 2010, and every 2 years the school has run. And now this is a new endeavor called the African Strategy for Fundamental Physics and Applications. And we are honored, both the African Physical Society and the African Light Source, that the launch will be here at this virtual workshop. So I will pass the microphone to Dr. Asama.
Thanks, Tabitha, for the introduction. So I am Kitevi Asamagan. I am originally from Togo. I am currently at Brookhaven National Laboratory. I am a physicist, experimental physicist, doing particle physics research. So today I will talk to you about a new project that we are about to start. We are starting the African Strategy for Fundamental and Applied Physics. Here are my colleagues from the steering committee. We have Professor Cornell, Simon Cornell, who just spoke about the African light source. We have Professor Farida Fassi from Mohammed V University in Rabat, Morocco. Professor Shaban Khalil from the Center for Fundamental Physics, Zewal City in Egypt. And Dr. Ferouz Malek from CNRS and Grenoble University in France. You can see more detail about this African strategy on the website. There's more information there. When you have some time, please go and browse. All right, so the outline of what I am going to say is as follows. I will tell you briefly about the motivation for this strategy and what are the expectations and the organization and so forth. And I will also tell you about how you can get involved. So this is not, you know, an effort of some people and then you can be on the side. But we are launching these things so that we want your involvement, your active participation. So that's exactly the point. We also briefly talk about the timeline and the physics group and subgroup and the endorsement and support and current status and our international advisory committee and the conveners. So the African strategy is not anything new. Around the world, there has been already many physics strategies that have been going on. In June 2020, there was an update of the European strategy for particle physics that was released. So if you take a look at that, you have this statement in there. The European strategy for particle physics is the cornerstone of Europe's decision-making process for the long-term future of the field. Mandated by the European Council, it is formed through a broad consultation of grassroots particle physics community. It actively solicits the opinion of physicists around the world, and it is developed in close coordination with similar processes in the US, excuse me, in the US and Japan, in order to ensure coordination between the regions, optimal use of resources globally. Now, this was actually a follow-up to previous two European strategies in 2006 and 2013. At the moment, the United States is preparing its own strategy, is known as SNOMAS 2021, with a final report expected by October 2021. I won't read, but it's similar philosophy. Latin America is also preparing its own strategy. It's called Latin American Strategy Forum for Research Infrastructures for High Energy, Cosmology, and Astrophysics. And the statement there is that they are developing a strategy to strengthen Latin American scientific collaborations and their impact. It is the first time they are doing it. They started in 2016. It is quite advanced now. In Europe also, there was the European Astroparticle physics strategy, which was released a couple of years ago. So you see that different regions of the world are getting the physics community together to try to define some sort of a roadmap, some direction, prioritizing resources, and putting all of these things into a report, which then they submit to their policymakers to help the policymakers plan how they want to support these resources and so forth. So that compelled us in Africa to come together and try to do something similar. And that was the reasons for us to start thinking about the African strategy for fundamental physics and applications. So we would like to develop a strategy to increase African education and research capabilities, improve collaborations, and inform international partners, sponsors, policymakers on the strategic directions likely to impact development in Africa. So it is us who should define what are the directions that are important for us, so that our international partners, when they want to partner with us, they know what we believe are the most important, what have priorities, because we have defined it. That is the objective here. So we want to engage African scientists and the international community in developing this strategy. So everybody, as physicists, needs to come together, express their voices, their opinion, and so forth, so that we can define what the strategy should look like. So it's a process that should take a few years, so it's not really indefinite. And at the end of that process, we release a report which will suggest the direction with actionable items for the next decade. And then that report will be submitted to the African policymakers, and then they have an information that, okay, this is what physicists, African physicists, in consultation with international partners, are thinking this is important for them. And then they will be able to act on it. And then the process could be repeated 7 to 10 years later. At that point, we will review what was done before, which actions were taken, which were not taken, how do we revise the strategy, given current information and so forth. I told you in Europe, they have done a third one, 2006, 2013, and then 2020. So that's the process. They have been reviewing it and updating it. And once we start, that's what we will be doing in 10 years or 7 years or however often we set out to be able to do it. So the general structure that we are thinking about is more or less the same thing as the other strategies of the world. We have a steering committee, I mentioned it to you, an advisory committee, and then we have to define the physics group that are of importance, and then the group conveners and so forth. At that point, we want to solicit input from the community at large in forms of letters of intent, which would describe what you think should be the physics priorities for Africa. White papers, which will be a bit more detailed than compared to the letters of intent, where you have done a bit more studies to demonstrate why you think this direction is most important for Africa. So all of those ideas should be discussed in the relevant groups or subgroups. And then we will be getting feedback from the International Advisory Committee in order to push the process further. That requires some logistics in terms of having websites and having some pages for working groups, repositories, mailing lists, discussion forums, meeting agendas, maybe workshops. All of these things are under development right now. So this is how more or less everything is connected. The steering committee will be the go-between, the one driving the efforts, communicating with the International Advisory Committee and communicating with the working group, making sure that everything is evolving according to plan, and will be responsible for drafting the final report. And the International Advisory Committee will be reviewing the progress, making sure that we are on track, and will be advising us on the scope. And also will be engaging with the international committees and communities and policymakers. And also in the end, they will review the final, review and endorse the final report. Then the group conveners will be the people who will be coordinating the efforts at the group level. So that will be defined according to major physics directions. And then there will be some topics that are cross-cutting That means they don't necessarily fall within one physics group, but they impact many different physics groups. For example, when we talk about physics education, for instance, yeah. So if you are in astrophysics, you have an issue to educate people about that. If you are in medical physics, you also have an issue about physics education. So that is cross-cutting. Yeah. So we need people who will be liaisons among the groups to make sure that there is no hole in our strategy. Everything is well covered, and that the groups know what is going on in the other groups. And then, so like I said, the timeline will be in a few years, we should stop. So how can you get involved? Well, you can get involved by nominating subgroup conveners. We will call for nomination at some points and these liaisons. You may volunteer yourself to be a subgroup convener. You may submit a letter of intent. You may submit white papers to tell us what you think is the most important direction that we should take in this particular field that will be relevant for Africa. And you should participate in drafting or developing these white papers. Also participate in the meetings that will be organized by the conveners, physics group conveners or subgroup conveners, and offer constructive opinions and your expertise. So we want your active participation in the process because it's a grassroots process by physicists themselves. Yeah, and also we would like to state that you know, we should encourage, or you should encourage, institutional credit for those who are working in the strategy, because it is really important for, you know, Africa as a whole. Like people who are in leadership role as conveners or liaisons, those should be recognized by the institutes that they have been called to do this job, and therefore they are getting credit for it. If you are working on the white paper, that should be of a publishable quality, and we encourage you to publish that in a peer-reviewed journal. And then your findings in your white paper, which may be or may have been published, those findings will be reviewed in the group and then will be referenced in the strategy report. So your work in this strategy will receive proper recognition at your institute internationally and should result in a paper and serve the interests of the African strategy. So it's not a wasted effort. You get a paper out of it, you get the recognition, and you serve the interests of the strategy. So here is the timeline. We are just about to start. If everything goes well, we should have that final report in October, December 2022. But we will revise this timeline according to progress. It may need to be adjusted. We will at some point put a deadline to receive the LOIs and the white papers, and as we make progress. Yeah, so here's the physics group that we have identified so far. I think there are 10 of them here. We are expanding this to add additional groups. So these are the ones that I mentioned here. So you should be able to find your group here, that you are also a part of this strategy. So come and join us. Let's get this work done. And we also have community engagement, which has topics like physics education, knowledge transfer, entrepreneurship, physics communication, outreach, stakeholder relations, government policies, and so on. Things like that that are not necessarily physics, but have a serious impact on physics. So those we have under community engagement. So we are thinking of having working group according to these major physics groups that we have here, and 3 to 4 co-conveners per group, depending on the group. We are in the process of selecting the group conveners. And in this process, it is serious that we have gender balance. And we will also seek additional, divide the groups into subgroups appropriately. So in terms of endorsement, we are developing this strategy under the umbrella of the African Physical Society. Professor Waynegate just mentioned that. So you go to the African Physical Society website, you'll see a link over there, and we will be reporting progress at meetings organized by the African Physical Society. And the society will endorse the final report. We also have support for already from international organizations like the International Union for Pure and Applied Physics. And we have support from the CERN Director General. We are in the process of engaging the African Academy of Sciences in order to be able to reach the African Union. We have support from the members of the International Advisory Committee. The current status is that we have a website under development. We are setting up the logistics. We had the first meeting with the group conveners and also with the advisory committee. We receive a lot of feedback and suggestions. We are in the process of implementing those. And we will be engaging the conveners in the definition of the subgroup for each group. That process will start in the next week or so. And then there are some invitations that we need to follow up on, and we'll pursue our engagement with the African Academy of Sciences with the aim to reach the African Union. And then there are the additional physics group that I mentioned on page 8. We will seek the group conveners for those physics group. And tentatively, before the end of this year, we aim to have another meeting with our International Advisory Committee and also the conveners. For the rest, we'll just follow the timeline that we described already. So here are the name of the people that we have identified. So if you stare at it a little bit, you'll see that these are people of international standing, and they come from Africa, Europe, the Americas, and Asia. And they have a broad expertise in their fields, and their job is to really inform how this strategy should develop, so that we do a good job in the end. So in terms of the conveners, like I said, we have 3 or 4 per group. Here are some of the people that we have identified who have accepted for each of the group. And you have particle physics there, you have nuclear physics, you have accelerators, medical physics, light sources, then you have instrumentation and detectors, astrophysics and cosmology, computing, and then you have the community engagement. Yeah, and like I said, there are the other physics group that we have, and we haven't yet advanced in finding the conveners, but that process is starting. So if you don't see your field in these 3 lists here, you mustn't be worried. The list that you should be seeing is on this page. If there are other fields of physics that you think are important that are not mentioned here, then come and tell us. But these are the major fields. Like I said, we will be defining their subgroups. So we would like your involvement in this process. You have our email there. Let us know your comments and how you want to help, and let us get this important work of the strategy off the ground. This is the inaugural one. If we succeed with this, then we'll establish a way forward. Other generation, younger people will come in and will do the updated version 10 years later, and other people will carry on. Just like it's being done in Europe. Like I mentioned, they started in 2006, and in 2010, they were doing the 3rd version. The US did one in 2013, and now they are doing a second one in 2020. Latin America is starting their version. Their first one right now is fairly advanced and is certainly a success. So we can also succeed in Africa. I will stop there.
Okay, well, we thank you so very much for this presentation, Dr. Asinagan. And in the interest of time, I will limit the Q&A behind your presentation. I think that everyone feels the importance and the gravity of the pulling together this strategy for fundamental and applied physics. And what I want to do is point you to the chat. The chat is really blowing up. So many people are engaged in this topic and asking you to add topical areas such as condensed matter physics, such as earth physics and agricultural physics, and such as biophysics, which is, they say, broad, Dr. Kruger says, is broader than medical physics. So you will have many, many ideas in the chat. With that, we are running behind by about 3 minutes. If there is a burning question, please go ahead and unmute yourself and ask. And if not, we will begin to transition to the next presenter. So I want to invite the next presenter, Professor Kwabena Frimpong Boateng, and he will address the environmental science, technology, and innovation. And I welcome you to begin sharing slides. And I want to remind everyone to continue to be engaged, and though we are capturing the chat, and your comments will reach the appropriate presenter to whom your question or your comment or your concern is directed. So do I have Professor Kwabena Frimpong Boateng?
Yes.
Okay, wonderful,
you,
wonderful. So if you have slides, I think you have to be made a co-host, and then you can begin sharing your slides. If you have no slides, then we will simply ask you to begin.
I don't have any slides.
Wonderful.
My job is to reaffirm Ghana's commitment to the African light source. I'm the Minister for Environment, Science, Technology, and Innovation. Before I became a minister, just about 4 years ago, I was CEO of the Kolebu Teaching Hospital and also the head of the Department of Surgery, University of Ghana Medical School. I trained as a heart surgeon. And so I'm speaking here not only as a politician, but as a scientist interested in this project. Let me first of all commend Professor Conner, Chair of the African Light Source Foundation, for his sterling leadership. Professor Conner, you and your staff at the foundation have kept the light shining on this difficult but important journey towards the establishment of the first African light source on the continent. Of course, what is happening today is also part of the legacy of Professor Alote, whom I work with at several levels in the university, at the Academy of Arts and Sciences, and also his work at the African Institute of Mathematical Sciences. So this is also part of his legacy. Ghana has produced some notable scientists who apply their expertise in the field of X-ray crystallography. Professor Geochemical, a former Vice Chancellor of the University of Ghana, Professor Baita, Professor Kingsford Adabo, Professor Friedrichs Phillips, and Professor Kingsley Buabasa are all known to have contributed richly in training the next generation of researchers in these fields here in Ghana. It therefore comes to us naturally to support the African Light Source project that has the potential of contributing significantly to the African science renaissance, thereby preparing Africa to the next level of development. Actually, I'm very happy to see a lot of young Ghanaians on this platform joining in this virtual meeting. I see Dr. Uduahin, Collins Akosa, Elliot Minka, Francis Nkrumah, Grace Jan, Joanna Hodasi, Joseph Asare, Kenneth Evans Lutrot, and Seth Santi, and others. And as you mentioned earlier on, Ghana hosted the African Light Source Pan-African Conference on Crystallography from 28th January to 2nd February 2019 in Accra. Prior to that, on the 15th of January 2019, I presented an information paper to Cabinet to inform the President and my colleagues about the conference, the importance of the African Light Source Project, the scientific and technological development of Africa. Following the hosting of the African Light Source Conference, some members of the planning committee in Legon at the University of Ghana began to work with government to develop conference outcomes to position the Light Source Initiative as a flagship regional project for the Ghanaian government under the leadership or championship of the President of Ghana. The government of Ghana, through the Ministry of Environment, Science, Technology, and Innovation, wishes to adopt the Light Source project and develop a narrative that places the light source within Africa's historical development, similar to the South Africa's SKA project. In this regard, the Ministry of Environment, Science, Technology, and Innovation, in collaboration with the University of Ghana, has set up an office for African light source affairs. This office will facilitate discussions and engagement with other entities that are interested in matters of the African light source. We will explore the possibility of linking our scientists to their colleagues working in light sources overseas. Strategies will be developed to educate the scientific community and future scientists about the importance of the African light source project and the role it will play in Africa's development. Education material will be developed for students in high schools. This office will also provide the necessary information to support the President's efforts to place the African light source project as a continental imperative on the agenda of the African Union Heads of States. So let me thank you all for organizing this conference. I recognize the pioneering role of Amadou, you and all of you at this meeting. We in Ghana are prepared to support this project, and our president is very much interested in it. Thank you, and God bless you all.
Thank you very much, Professor Frimpong-Boateng. We appreciate your remarks, and I will take a moment to pause if there are any questions, and invite everyone to type the questions in the chat. And as I've said before, your questions and comments will be sent to the speaker to which those are directed. And we are very excited to have the support of Ghana, even at the level of the president. And thank you very much. This is very exciting. Okay, so we are running a little bit, actually we're just on time. And so I will invite our next speaker to begin sharing screen. This is Dr. Mansai Dialli, who will give us our first technical talk of the session. And this talk is Synchrotron Radiation-Based X-ray Studies on Energy Storage Materials, a Case for Hematite. And so if we can have Dr. Dialli to begin to share screen, and then we can begin with this talk. And it is a 30-minute technical talk. I want to thank all of the speakers this morning's session, and I also want to acknowledge our sponsors, of which you will see a little bit later, and ask that after the sessions are over that you just remain behind a little bit so that we can show you our sponsors represented by their logos. And so, Dr. Dialli, we can see your slides now, and I will begin to mute as you begin to speak and to present.
Okay, let me just share. Are you sharing? Are you seeing the slides now?
Yes, we are seeing your slides.
Okay, so we are there. Good afternoon, everyone. It is actually a great pleasure to be invited by all of you, great scientists who have been there for me, before me, guiding me to be where I am today. And I really appreciate this opportunity. Thank you so much to Professor Canal, who is the chair of the African Light Source, who has always looked for me to be involved in this work. And I am really very, very happy to be part of the whole organization. I'll speak on synchrotron radiation-based X-ray studies, but then I want to make it clear that I realize that I'm speaking tomorrow and it's just like I'm going to speak exactly the same thing, but I'll try not to be too technical now so that tomorrow I can become deeply technical. All right, thank you so much. I just want to remove this here, okay. Yes. World synchrotron radiation facilities. If you look at this map, you can see that definitely in Africa, we don't have anything. And whilst we don't have anything in Africa, and all the people who have spoken about what is that you can do to move Africa forward, you look at USA, it has got 14, EU has got 17, UK has got 1, Japan 5, Russia 5, Italy 4, China 4, Singapore 1, Thailand 1, South Korea 1, and Brazil 1. And you realize that if we want to move forward in scientific research, we really need to invest in this synchrotron radiation. So my experience have been that if we go into newer techniques, we are able to find new solutions to world problems. And in particular in Africa, we are being always used as gimmicks for experimental work. And whilst we are doing that, we can do it ourselves. Omar, what happened now? Okay, right. We would want to have an African light source, and I just want to talk about what will be the advantages of having an African light source. According to the United Nations Sustainable Goals, we have issues with energy, equity, we have issues with food, we have issues with water, and we want to say that we'll be able to achieve that in the near future. And I wonder if that is possible. In the energy, water, food nexus, where everybody else in the world thinks that they should be bringing aid to Africa so that we can have food, whilst we have got so much land that we could be using to grow our own food, and so much water in the Congo River, for example, and energy, investing in renewable energy whilst we are doing our research. So the African light source has got very, very big advantages for us in Africa. And it will bring just one light source at one point, it will be able to bring us a multidisciplinary research facility. An example is what has been done at Berkeley Lab for COVID-19 and related diseases. They use the light source to find some results which they think are excellent results for COVID-19. And they use the advanced X-rays to map out the 3D structure of proteins relevant to diseases at a scale of molecules and atoms at these laboratories. At Argonne Labs, they have used the photon source, which is also a kind of a kind of a synchrotron radiation, a bright light for drug delivery, and they were able to use molecular X-ray discovery, a crystallography, so that they can come closer to an effective HIV vaccine and addressing a number of diseases that are very rife here in Africa. So we started this journey with all like Professor Canal going to a European synchrotron radiation facility. And I like what they've written on their website. They say they're unlocking the secrets of matter. The ESRF state of the art in synchrotron provides the international scientific community with unique opportunities for the study of materials and matter, addressing global challenges like COVID-19. What's wrong? Can you hear me? Bringing nations together because it's an international facility. And South Africa is one of the countries that are collaborating with this synchrotron radiation of science and innovation. At this facility, using the high resolution near field synchrotron photographic X-ray, they were able to map out the 3D, the material was, they detected the ultrafine detected microstructure of titanium iron-based alloy. So this material was produced by additive manufacturing, exploiting the high solidification rates of laser-based 3D printing. And they were also able to do this one for the heart, the kidney, three-dimensional image of kidney and unprecedented quality have been obtained with a simple, cost-effective of sandpaper as an optical element to X-ray imaging beamline. And when you are working with such, I believe that for us in Africa, we can be able to do something about all our problems, finding cures, bringing major breakthroughs in material science and life sciences. As what we're doing. We have visited this research facility, Elatra, in Italy, and there are lots of opportunities for African students. One must just go into the ICTP website and go into the Elatra website and be able to see the opportunities that are there. And also another organization called CISA there has got that kind of facility. And this kind of facilities will help us to reduce the African brain drain for our people who goes to Europe or to Americas to do a PhD, and they cannot come back because there are no facilities for them to continue with research. So this energy issue will give Africa an opportunity when we are continually investing in different research opportunities like this, the light source. So I'm looking forward to one day finding a light source in Africa, which can be very usable for all of us. In this picture here, you have got two storage facilities for solar energy. One is the batteries here, and the other one is hydrogen. And I am focused on hydrogen, but tomorrow I'll also speak more on both hydrogen and batteries. So what is synchrotron radiation? Synchrotron radiation is emitted by charged particles traveling at speed relative to the speed of light when accelerated by magnetic fields. So these were first observed in synchrotron and synchrotron light, now produced by storage rings and other special particle accelerators, typically accelerating electrons. And it is able to produce giga electron volts of energy and lots of energy using the basic electromagnetic studies that we do in high school. This is a ring, you know, when you work with Zoom, you start doing wrong things. This is a ring that represents a light source in which electrons are. It's a cartoon that shows that electrons will be accelerated throughout here, interacting with the magnetic here, and storing the energy that is being created by this acceleration of electrons. So the experimental techniques and usage of this synchrotron light radiation. We all have XRDs in our vicinities where we can work, but these are very limiting. So synchrotron light is an ideal tool for many types of research in material science, physics, and chemistry, and it is used by researchers from academics, from government laboratories, and industrial places. We go to the synchrotron radiation facilities to explore the materials. Like here, when we're working with mining materials, you can take it to a synchrotron-based radiation facility where you'll be able to see more of what is contained in that material. So several methods take advantage of the high intensity, tunable wavelength, collimation, and polarization of synchrotron radiation at beamlines, which are designed for specific kinds of experiments. And I'll speak about these experiments now. One of those experiments is scattering and diffraction. So we know the XRD and scattering experiments are performed at synchrotrons for structural analysis of crystalline and amorphous materials. So this application to material science. So the measurements may be performed on powders, single crystals, or thin films. The resolution intensity of the synchrotron beam enables the measurements of scattering from dilute phases or analysis of residual stress. So XRD, X-ray crystallography of proteins and other macromolecules like PKX or MX are routinely performed when you are using diffraction and scattering experiments. And in 2009, the Nobel Prize in Chemistry was given to this kind of research. And that's where you find your SXR, which is a single angle X-ray scattering for nanomaterials, and also the grazing incident small angle X-ray scattering. So these are all done in the synchrotron facility. Oh. This is the application of a result of structure of ribosome, which actually won the Nobel Prize using the synchrotron facility. So we can also do spectroscopy where you do XRF, or you do X-rays, or you do NEXARFs, and so many different related spectroscopies that are coming out of the synchrotron radiation. You know, I looked at the time, guys, and I saw 4:08. I thought it's 4:18, and I was scared. So we can also do imaging. Synchrotron X-rays can be used from traditional X-ray imaging, phase contrast X-ray imaging, and tomography. If you always regularly go to the lab like me, sometimes you get very frustrated that your image that you have found there is not very accurate. So you need to use a synchrotron facility like STXM and LIGA so that you can come up with very clear results, which we will be able to publish in very good journals. Like the previous speaker was speaking, that we need to be publishing in high impact factor journals. Wow, this is my favorite, hydrogen fuel. We have seen that already hydrogen is being used as a fuel in many different transport facilities. During the pandemic, the aviation industry was brought to its knees. And I think that gave us an opportunity to look at how we can do research in a different way to solve economic problems in our countries, which are actually energy problems. And then we can go and do the storage of solar energy using hydrogen fuel. But the problem that is still there is that many countries don't even have one station for hydrogen refueling. That's why we'll stay for a long time using oil-based fossil fuels. And many people want to argue with you and say, but what are we going to do with oil? We have many other uses of oil, which will not contaminate our environment. Hydrogen is extremely important. You use it in vehicles, you use it in synthetic fuels, you know, upgrading oil, biomass. You find it so in many different business opportunities and scientific opportunities, as you can see in this picture. That is, you can take your hydrogen from using some technology into your grid and start feeding different areas so that everybody has got electricity due to hydrogen, not fossil fuels. And we can also use the solar to store our hydrogen. Store solar energy using hydrogen, sorry. These are the few fuel stations of hydrogen globally. Japan, that smallest country, still has the largest number of public hydrogen fuel stations. and Germany has got 60, and USA has got 42. Other countries don't even have at least one. And we must look at the future of storing hydrogen as a fuel for our transport so that we can clean the environment. So our case for hematite. Some years ago, me and my colleagues, my colleagues in Switzerland at EMPA, published this paper called In Rust We Trust. Rust is the hematite, which is the red soil. And there they found, using synchrotron facility, they were able to observe 2 electron holes in hematite during photoelectrochemical water splitting. Another experiment by my colleague Dibaje Bora and Arthur Brown, using the X-ray diffraction facility, were able to publish this work on evolution of structural properties of iron oxide nanoparticles during temperature treatment at the Synchrotron facility. And evolution, the next one was evolution of oxygen near edge X-ray absorption fine structure, transition in the upper Hilbert band, where we were using the material in iron oxide for electrochemical oxidation. All right, this is the process for photoelectrochemical water splitting. You shine the sun on your semiconductor, which is a phonoanode, and then you create electron hole pairs where electrons are attracted by a bias to the platinum counter electrode. And then this blue here is the water. And we say at the photoanode, the hydrogen, the oxygen is involved, and then at the counter electrode, that's where we produce hydrogen. That's why we speak about water splitting. We take energy and we apply it into water using the device that comes from a semiconductor and a platinum electrode, and you produce oxygen and hydrogen. What you are going to do is oxygen, you throw it in the atmosphere, you reduce the amount of carbon dioxide that is already destroying our environment, and you collect hydrogen for your transport issues. So our material that we want to use, that we are using in my lab, is hematite for photoelectrochemical water splitting. Semiconductors that are being used here have got certain requirements. It must have a suitable band gap to be able to absorb the solar light, and it must have suitable band positions, which I'll explain quickly, and then it must have low overpotentials and efficient charge transport and stability in water. When we look at the band gap, you find that actually natural solar radiation consists of 5% ultraviolet light. So it becomes difficult for you to use a material with a bigger band gap, a band gap that absorbs in the ultraviolet light, 43% in the visible, which takes most of this, and that's what we need, and 52% in infrared radiation. So these are the band positions. That's your conduction band, and that's your valence band. This is your hydrogen production position, and that's your oxygen production position. You must be able to find a material amongst all of these materials that you see here. People have used them and they are published. But when you look at them and you look at the band gaps, silicon has got a nice band gap, but it is not stable in water. Cadmium selenium, it has got a problem of cadmium will be dissolving easily in water and is poisonous. Silicon carbide is too wide. Gallium arsenide is suitable, but gallium arsenide is not stable in water. And then zinc oxide may be a bit stable in water, but the band gap is too big, so it will absorb very little of the solar energy. We are trying copper oxide, but copper oxide is not stable at all. The most attractive material amongst this is iron oxide, which we call hematite, which has got a band gap of 2 electron volts, which will absorb almost 40% of the visible light, and it is stable in water. A simple illustration of how iron oxide is stable in water is that if you go to any place where there's nice flowing water, like a river where it's not very deep, you'll find stones in there. And those stones on their surfaces is iron oxide. And the iron oxide is able actually to grow algae on top of them, which means that iron oxide is very stable in water, but iron oxide has got its own other problems. And let me just quickly run because now I'm running out of time. So I will speak about these things more tomorrow. So when we look at iron oxide, hematite, the advantage is that it has got that small band gap, is relatively abundant, therefore it is cheaper to use, it's chemically stable in aqueous environments, and it has got a suitable position for oxygen evolution reaction. And the disadvantages is that it is a poor conductor of electricity. It has got its short lifetime of excited carrier charges, poor oxygen evolution reaction kinetics, and a very short diffusion length. And what happens with the very short diffusion length is that iron oxide, when electron hole pairs are created, they will recombine very quick. So we have made this iron oxide using solution-based method, hydrothermal method, spray pyrolysis, and all of that. And we have built this in our lab. We have them in our lab. We have found that if you use nanostructuring, doping, heterostructures, modification with co-catalysts, and the plasmonic and Asmret with metal nanoparticles, we are able to improve photocurrent using hematite. Therefore, whilst we are improving hematite photocurrent, we are still putting together a good review that will show that this nanostructuring, which should be used in the hematite, as you grow hematite to produce nanostructures, that you can go to your synchrotron radiation and see the finer structures of these nanostructures. And other people like Kevin Sevula have done that with Dibaje Bora and Michael Gratzer whilst we're using it for hydrogen production. These are the nanostructures that we have achieved in our labs: the dendrites, nanoparticles, mesoporous phases using deep coating, the cauliflowers, the nanocones, and all of this. Whilst we have achieved them in our lab, we don't claim that we are the first people to achieve that. Other people have achieved that. Chair, how much time do I still have?
You have a total of 9 minutes left. Of that, you may want to leave time for a few questions.
Thank you. I was just worried that I don't have to take a lot of time. So we have prepared hematite, and then the photocurrent density. We have looked at the photocurrent. These are our results in our lab. For the bulk hematite using electrodeposition, the photocurrent was 0.5 volts versus mercury hydrogen oxide in 1 mole of sodium hydroxide with applications of 1 sun. And in all of this, we have used 1 sun from our solar, okay, whatever. Then we have also achieved nanoparticles, and you can see that our photocurrent is growing gradually from the 0.5 milliamps, 0.9 milliamps, 1.3 when you use nanorods, after we have grown those nanorods using hydrothermal methods. And then with our nanoflakes, we have just achieved an experiment where we have made the nanoflakes, but the photocurrent is too small. But another experiment in the lab where we used the nanoflakes, it was improved a little bit, but we still believe that the nanotubes and the nanorods are doing better as compared to other nanoparticles. When you use suitable impurities to dope your hematite, you find that you are able to improve the photocurrent output of the hematite nanostructures. We have used manganese, we have used gold, we have used sulfur, we have used phosphorus. And in all of this, we have found that the photocurrent is changing in differently in milliamps per centimeter squared, with the highest photocurrent being 0.74 when we have doped with sulfur, but we have not yet proved whether this with sulfur is not poisonous, or will it be able to succumb the damp environments where we are using our devices. Okay, let me just quickly run. We have used the catalysts like iridium oxide, and we have co-doped with cobalt, and this is actually platinum, sorry. And then borates like nickel, bismuth, and oxyhydroxides. So in plasmonics effects, we have deposited nanoparticles and metal nanoparticles onto the hematite and studied the Schottky barrier behaviors of the photoelectrochemical device, which we will now put in water and look at if we are improving in that kind of work. So the work that we have done in our lab is when we were varying the different methods with using either deep coating or spin coating or combining the two. And the results, let me just go to the photocurrent results. You can see that when we have used the deep coating, what is that? The deep coating is here in A, and then deep spin coating is in B, and then combined spin coating, deep coating methods were not giving us best results. They were very bad. But then if you take one of the two, you find that you are doing much better. Another experiment is that we have established in our lab the electrochemical impedance spectroscopy, where we are able to do measurements on the impedance spectroscopy measurements for the hematite in water or in a aqueous solution. And we are able to produce very nice results that you can see here for dark measurements and for the light measurements using either a combined coating or deep coated methods. Many of the people out there are still using only deep coating methods, and we have published this paper on influence of coating techniques on the optical properties and structural properties of hematite thin films. The other one was how we made our nanostructures. As you see it here, I just want to rush quickly. And then the pictures here shows you that we're able to find the nanostructures with very little diameters, like 31.2 for this materials, hematite. And then we did the annealing studies. And then in the annealing, as you see here, we have used our normal XRD, and we would be very happy to go to a synchrotron facility and do these measurements again and see what we get in situ measurements when we are using this. When we did our annealing studies, we found that you can anneal hematite from 500 to 750, but if you go to 800, something else happens, which is an example of the dislocations becoming bad in this material, when you anneal at a higher temperature, so that there is traps and defects that are trapping electrons during the electrochemical measurements.
Dr. Diale, we are down to the last 3 minutes and you have many questions in the chat. So if we can wrap up a little bit sooner.
Okay, let me wrap up this and not go further beyond this. Let me say we have achieved copper oxide onto hematite as a heterojunction structure. And yeah, our photocurrent continues to improve. So these are our list of publications for all the work that we have done in the past since 2014 up to now. We have been doing this research since 2014, but we started publishing actually, I think in 2016. I want to say in summary, if you want to use hematite, strategies for nanostructuring are very important. And there is deep coating, and there's photocurrent measurements that improves as you use these different strategies. And then we believe that with heterostructures, with copper oxide, when we have established that copper oxide is stable, we can do much better. You know, I call it CuO, copper oxide, that way, because, you know, I'm not a chemist. I continue to do all those wrong things. I just want to acknowledge the University of Pretoria for giving me the enabling environment to grow in the research that I've done, water splitting and producing hydrogen, the National Research Foundation, which is funding my chair, and the Motsepe Foundation that is giving me private money. Thank you. Thank you for listening, everyone.
And thank you for a very wonderful talk. You have many questions in the comments. In the interest of time, and I realize I ran over by 5 minutes. I told you a time that was longer by 5 minutes than published. We will just run the entire session over by 5 additional minutes. I'm going to ask that Dr. Asmret Berge begin to share her slides for the next talk, while we will take one question from the chat. One question from Daniel Wamwangi is saying, great talk, Dr. Diale. What are your thoughts on multiferroic materials such as bismuth ferrous oxide as thin films with large surface to volume ratios? If you can comment on that in just a few remarks.
Can I see the question, please? Where is the chat? Oh, okay, it's here. Daniel, how are you? I'm good to hear. You know, you are such my neighbor, but you know, it's difficult to see each other.
Okay, yes, I placed the question into the chat and it comes from Daniel Wamwangi, and it says, it asks you your thoughts on multiferroic bismuth ferrous oxide.
Oh, okay, on bismuth. Bismuth has achieved some kind of a photocurrent, but it has not been good with hematite due to its position for band gap alignment for hydrogen production. If you look at my slides, I think somewhere in that big, let me see, where is that slide? Sorry, everyone, that is a slide, okay, that we just, yeah, this one. Okay, we can close this chart from here. How do we do it? Oh my.
Take your time to figure that out. Just go to slideshow, I think. Go to play at the far right. I think you have a play button at the upper far.
Okay, thanks. Bismuth has not been used here, but with the dope, when vanadium oxide is doped with bismuth, that's when people have reported something there. But because of its position very far from hydrogen evolution band gap, and also very far from oxygen evolution band gap, it is still found to be non-suitable. But we hope your guidance can help us to make bismuth oxide, but we will make it a heterostructure with hematite. I'm just sold out to hematite.
Okay, well, we thank you again for a very wonderful talk, and you will see in the chat window, there are many compliments to your talk. At this time, I will call forward, and my apologies for allowing the time to lapse, and I hope that everyone can continue with us until the very end, and a little bit, maybe 5 or 10 minutes over the end of the published meeting time. At this time, I call forward Dr. Asmret Berge, and it looks like we have crossed into a new session, and I wonder if I'm the session chair, should I be calling forward a new session chair also? But in the interest of time, I'll go ahead and begin to call forward the next speaker. I don't want to skip any of our session chairs. I need to.
Michael Fodger, it's
Yes.
as on the web.
I don't know if you can hear me.
Oh, wonderful. Dr. Michel Faugier is the session chair. I will call him forward to introduce the next session.
Yes, hello everyone. I'm Michel Faugier from the Canadian Light Source, and I'm honored to convene this session. Our next speaker is Professor Asmret Berge from the University of California at Merced. Asmret has a Bachelor of Science degree in Soil and Water Conservation from the University of Asmara in Eritrea, and a master's degree in political ecology from Michigan State University. And then she did a PhD in biogeochemistry at the University of California at Berkeley. And her research is focused on understanding the impact of environmental conditions on soil processes. And she has been involved in quite a few global initiatives like the Millennium Ecosystem Assessment that was commissioned by the United Nations. And she's also an advocate for women in science. Her talk is understanding the effect of changing environmental conditions on vital soil processes. So please go ahead and start.
Thank you. Can you hear me well?
I can hear you.
Perfect. Thank you. Thank you for the organizers for the invitation and the generous introduction. I realize this is quite a switch of topics for most attendees. But I'm really glad to be sharing my work in soil science with you all. As Michelle indicated, I work on soil science. I'm a soil scientist by training, and most of my work deals with biogeochemistry, meaning the cycling of essential elements between the soil, the atmosphere, and the hydrosphere. Today, I'll focus my talk on phosphorus dynamics in soil and in particular dust. And I'll tell you some stories from data that we've collected using ZANES. And I'll try to give you a brief introduction to the kind of work that I do, just so that we're all on the same page as we start. Before moving forward, I would like to acknowledge that I work as part of a very dynamic interdisciplinary team, including my current PhD student, Morgan Barnes, and collaborators that are listed on the slide, which all deserve credit for this presentation and the work that I'm going to be discussing. Okay, so generally speaking, the kind of work that we do in my lab deals with, as I mentioned, these biogeochemical cycles of essential elements, in particular carbon, but also nitrogen and phosphorus. And a lot of times we deal with also this Pi-C pool that I refer to on the screen, which is a pyrogenic carbon or fire-altered carbon that is a product of wildfires in the environment. And we spend a lot of time thinking about what happens to these essential processes that cycle the nutrients within the soil system and between the soil and the other spheres when there is sudden rapid change in environmental conditions. It seems like somebody's having connection issues in the chat. Hopefully, I'll try to slow down. Hopefully that will work. So we try to study what happens to these essential processes when there is sudden change in environmental conditions, in particular things that happen during erosion, when erosion laterally redistributes topsoil in the earth system, when fire causes combustion of biomass and deposition of these fire-altered carbon as a partial product of combustion of biomass, as well as, as a product of different global change variables that have to do with changing atmospheric temperature or changing the amount, distribution, and pattern of precipitation globally. Because all of these things introduce a very sudden change in environmental conditions that produce the soil and that govern the cycling of these essential elements. So we've concerned ourselves a lot about the vertical and lateral transport of topsoil and associated organic matter within the soil system, as well as export of topsoil material from terrestrial to aquatic systems. We spend a lot of time thinking about how natural nanoparticulate minerals, in particular metal oxides of iron aluminum oxides and hydroxides and oxyhydroxides, how they stabilize organic matter in soil, make it less available for microbial processing and decomposition, and how they govern key soil processes, how those interactions govern key soil processes. And then at the larger scale, we think a lot about the role that soil plays in human society, in particular, this resource, the soil system that humanity as a whole refers to, we depend on the soil system for roughly about 97% of all the food that we eat. At the same time, we derive a lot of our needs for feed, fiber, and a bunch of other things also on soil. But this resource base that we need for humanity to survive and thrive is currently compromised in a major way because of human actions. So we've spent a lot of time thinking about what does this mean for the fate of humanity going forward, in particular for national security type of considerations. And with all the work that we do in our lab that spans multiple spatial and temporal scales, multiple traditional wet chemistry approaches, kind of association biochemistry type of work, as well as more introduction of advanced spectroscopy to be used with soils. We've tried to practice principles of justice, equity, diversity, and inclusion to make sure that everybody gets represented in the kind of work that we do and is welcome to do this kind of work in academic institutions. Okay. And I'll structure my talk in a way that I'll talk about phosphorus speciation in soil in particular in the first section, and then I'll talk about phosphorus in dust, and end with some concluding thoughts. Okay, so to start with, I'm concerning myself with phosphorus in particular because it is one of the very essential and major macronutrients in soil, meaning it's needed in large quantities for plants to complete their physiological cycles. It's a critical element needed for a range of cellular and genetic processes, key for energy transfer processes in biological organisms, as well as structural support for plants. So essentially what it means is that if plants do not have access to enough available phosphorus, they cannot complete their physiological cycles, they cannot produce the food that we want them to, and photosynthesis and a range of associated processes will be hampered. But the biogeochemical cycle of phosphorus is one of the most complex that we know of. For plants to be able to use phosphorus, first it needs to be available in the form of phosphates in soil solution. But there's a lot of competition for that phosphate in the soil that could enter into soil solution because to start with, the primary source of phosphorus is only phosphorus-bearing rock minerals, in particular this mineral called apatite. And this mineral has to weather, it has to undergo both physical breakdown of the rock into smaller pieces and associated biological, chemical, and geological processes in the soil system, which we collectively refer to as biogeochemical transformations. Oh, I have audio interference from somebody. Okay, perfect. So these I don't know if you all can
Dr.
hear.
Burra, I'm going to take a moment to mute everyone, and then you should unmute yourself again. Simply, I
Okay.
can't find the person easily.
Okay, no worries.
And so now you can unmute yourself only, Dr. Burra. I have unmuted everyone.
Okay. Let me go back to this slide. Okay, can you hear me now?
I can certainly hear you. I'm going to mute myself now. No, I cannot hear you now. I'm unmuting you again. Ask to unmute. So I have asked you to unmute yourself electronically, and now I'm asking
I have done so.
And now I can hear you, and sorry for the interruption.
No worries, thank you, I appreciate that. So as I was saying, this biogeochemical cycling of phosphorus is a pretty complex process. There's a lot of competition for phosphorus once it enters into soil, because as it's undergoing biogeochemical transformations, first of all, plants can take it up, but also microbes can take it up in soil. But it could also be immobilized by sorption onto reactive mineral surfaces, in particular clay minerals, iron aluminum oxides, carbonates associated with calcium in particular, and others. And this sorption with the minerals makes it unavailable for plants. And so there's a lot of emphasis on phosphorus being available when you think about the phosphorus cycle, because a bulk of the phosphorus that exists in soil, typically 90–95% of the phosphorus, is not available for plants. Plants cannot basically desorb phosphorus outside long-term weathering processes that take a lot of energy. And so it becomes a key nutrient that controls plant productivity, a key nutrient that controls a range of biological processes in soil. And also important to note that the biogeochemical cycle the biogeochemical cycle of phosphorus is also complex, but because phosphorus only originates from this phosphorus-bearing parent material or rock as a product of weathering, but it also has no mechanism for biological fixation. What we're talking about here is basically that, unlike nitrogen, that microbes can form association with plants and soil to fix it from atmospheric nitrogen, for example, there's no atmospheric component in the phosphorus cycle, and there's no potential to biologically fix it. So it becomes an even more challenging nutrient that limits plant productivity. And this limit to plant productivity is also propagated into limits on the amount of carbon that plants and then the soil system can take out from the atmosphere. Keep in mind that the amount of carbon dioxide that's currently in the atmosphere that we're all worried about from a climate change perspective is mostly a product of fossil fuel derived carbon that was released to the atmosphere, but some of it is also derived from deforestation and land use patterns. And so it's carbon that was released from soil back into the atmosphere. But we also know that we could do the reverse. We can entice, if you will, or kind of help the soil system take up extra carbon dioxide from the atmosphere so that it reduces the atmospheric burden of CO2. But for that to happen, plants need to photosynthesize at their optimal rates. And then once those plants or the animals that consume the plants die, their biomass has to enter the soil, which is a beneficial thing for many, many, many reasons. But what you see in the charts that are on the right side of the screen is that the ability of plants to photosynthesize, as represented by NPP, or net primary productivity, in the top panel, and the ability of the terrestrial ecosystem or land to take up atmospheric carbon dioxide is increasingly constrained by phosphorus. So what you're seeing in the figure here is model projections of terrestrial plant productivity and carbon storage, where the black line represents how much plant productivity could happen in the top panel, or how much carbon uptake from the atmosphere to the soil, or net removal of atmospheric CO2 that can happen by land if there was no nutrient limitations. But the red box shows what would happen if we considered the fact that large parts of the terrestrial ecosystem is actually faces nutrient limitation, in particular for nitrogen. And the blue line highlights what happens when you consider the real challenges that most ecosystems have to face with phosphorus and nitrogen limitation for plant productivity. In case this did not become clear from my discussion, this is part of the reason why farmers around the world spend a lot of time thinking about fertilization to supplement plant productivity, because nitrogen and phosphorus are limiting plant productivity, and plants cannot grow optimally without those. So they spend a lot of time trying to find ways to supplement nitrogen and phosphorus to alleviate the nutrient limitation soils are facing. And this nutrient limitation then shows up in even our ability to mitigate against climate change, because doing so requires that we overcome this nutrient limitations, but we still have a lot of challenge in understanding, in particular, the phosphorus cycle. As I mentioned, phosphorus is this complex nutrient that's distributed in multiple different pools in soil, as you saw from that flowchart based phosphorus cycle before. And traditionally speaking, most people in the soil science, agronomy, and other communities that think about phosphorus availability in soil, sediment, or dust used to use this wet chemistry approach that's called the Hadley fractionation scheme. It's a successive, extraction scheme that uses different chemicals to extract phosphorus that's associated with different pools in soil. In particular, trying to identify phosphorus that is somewhat available to plants versus phosphorus that's actually locked away in mineral associations and is not available to plants. But part of the problem that we've had historically in our scientific community is that this successive fractionation scheme that I described, that's on the right in this figure, is actually not a very accurate way to represent how phosphorus exists in soil. You can have multiple pools associated with different types of minerals get extracted in different steps. And so the picture had remained very muddied, if I may, to basically cause major issues with misquantification of phosphorus availability in soil that has hampered advances in our understanding of the phosphorus cycle until now. But recent advances in adoption of X-ray spectroscopy, though, has allowed us to basically, we've spent a lot of time, and I have to give special credit here to my student, Morgan Barnes, and my collaborator, Mike Zhu, who've spent a lot of time in synchrotron facilities trying to develop very good reference spectra for phosphorus zanes, which they have to do by characterizing different types of phosphorus that they can find and imagine independently, as well as once the phosphorus is absorbed to mineral surfaces, both considering the organic and inorganic forms that phosphorus might exist in soil. And once they've developed the robust reference libraries, then we're now able to use kind of that information to quantify distribution of phosphorus more accurately in soil, in pools that are associated with iron, aluminum, calcium, which are unavailable, versus organic pools of phosphorus, and some phosphates that are more available to plants. And this technique, obviously, it takes a lot of time. It has taken a lot of energy, but it has allowed us to develop a better understanding of the phosphorus cycle using in situ non-destructive approaches that require, relatively speaking, minimal sample treatments. And the work that I'm going to talk about today was all conducted at either the Canadian Light Source or Stanford Linear Accelerator Center. Okay, so the first data I wanted to show you is on phosphorus speciation in soil, and trying to understand how phosphorus forms vary in soil along climatic gradients, in particular climatic gradients that constrain soil weathering intensity, or how processed the soil is, how different the soil is from the original parent rock that it was derived from, which is a function of climate, biological input, and a few other key environmental processes. So what you see in the chart on your right is this metric that we call EEMT. Is just measuring energy input into soil as a way of the kind of quantifying the extent of weathering a given soil has seen. Each one of the dots and each one of the symbols represent different sites that we sampled along two major observatories and climal sequences, or soils that vary in terms of the impact climate has had on their development on two sides of the Sierra Nevada mountains in California. And these are called the Southern Sierra CZO and the White Mountain, which I'm going to skip. But the main thing you want to see, I wanted to highlight, is the fact that there's huge variability in climate occurring between these sites that allow us to think about how phosphorus might be speciation might change, with climate, with weathering, and what kind of information we can get. And we've been fortunate to get this really wonderful data set that we're compiling on soils, on topsoils that is marked by A. It's how soil scientists describe topsoil. It's an A horizon. And then a B horizon is the layer that's right below it. And the C horizon is typically weathered rock that is not yet kind of the loose soil material that you recognize on the soil surface. And so we've been able, without going into too much detail, we've been able to see that as a function of weathering, as this EMT variable that I mentioned increases, we've been able to see shifts from calcium to all more iron and aluminum-based associations for phosphorus. And we've been able to kind of accurately quantify how phosphorus forms vary with climate, how phosphorus forms vary with climate and depth and weathering intensities in ways that we've never really been able to do with soils until recently. And this is now allowing us to rethink a traditional model that has been basically the way that soil science has viewed and understood phosphorus cycling historically, where as a function of pedogenesis, which is basically time since weathering started and how altered the soil is, the distribution of phosphorus was assumed to follow this kind of model that you see here, but the data that we've been able to get with Zanes is now allowing us to rethink that model, and we're able to see that first of all, phosphorus amount doesn't follow this traditional model, now that we're able to verify the different forms of phosphorus using Zanes. And there's even important differences that we're seeing with depth, but we are seeing maybe slightly similar patterns to the traditional model when it comes to speciation and distribution of phosphorus, in particular that shift from calcium associated phosphorus, which is common form in the rock that bears phosphorus, to more as weathering intensifies and the soil accumulate iron, aluminum oxyhydroxides, oxides, and things like that, that phosphorus starts more and more to be associated with them. And we're also seeing that the organic form in phosphorus is relatively affected little with weathering intensity. These are kind of shifting the paradigm of phosphorus cycling, if you will, in soil science, which has been great. And it's part of the PhD thesis of my student, Morgan Barnes, that I mentioned, who's getting ready to defend her dissertation in a couple of weeks. The next piece of work that is related to this is what happens when wind blows soil from the soil surface and transports it. And this is a really important mechanism that controls soil health, even environmental health and air quality in many parts of the world, because in particular in dry ecosystems, wind is able to lift a lot of dust, meaning pick up soil from the ground and transport it and keep it suspended in air for long periods of time. And we even know that dust is transported long distances globally, thanks to a lot of exciting work that's been happening in this field recently. This is, for example, a major variable in Africa, because the dust transported from Sahara has now been traced in many parts of the world, with very interesting implications for biogeochemical cycles of essential elements, including phosphorus. One of the things important things we're learning as we gain more and more understanding of dust transport and dynamics is that dust can outpace the supply of bedrock nutrients into soils in terms of available phosphorus, at least in the short term, at least in systems that don't have a lot of phosphorus in their bedrock, or are the way the soils are not weathering extensively very fast. And this is interesting and important because I told you early on that phosphorus availability limits plant productivity, the ability of soils to sequester atmospheric carbon and things like that. But we know that phosphorus cycling in soil is a very slow process that's governed, more by geologic timescales than human timescales. But dust transport is a rapid process, right? It could lift sediments from one part of the world and deposit them somewhere else a few weeks, if not, later. And that supply of phosphorus that's happening by dust in some ecosystems seems to be bigger in the short term than what weathering of rock can provide to the soil system. And we've also seen evidence that plants can pick up this dust transported phosphorus and use it quite readily. So this motivated a work that was funded by the US Department of Energy to allow us to monitor two ecosystems, one in more the central part of the US in Colorado, and another one in the western part of the US in California, two major mountain ecosystems, the Rocky Mountain and then the Sierra Nevada in California. And we were able to collect dust, painstakingly collect dust for long periods of time so that we can establish where the dust is coming from. So where was this soil before it was transported to the Colorado and California, and then be able to characterize it. There's a lot of interesting challenges, scientific challenges that arise with this, because to be able to accurately, first of all, identify where the dust is coming from, you need to collect enough material. And imagine needing to collect enough material to do all kinds of chemistry and physical characterization just from dust. It takes a lot of time, a lot of energy and patience. But once you do that, thankfully, we have tracer approaches, in particular lead isotope-based approaches that can relatively accurately pinpoint where that material was originally weathered in. So where was that soil before it was lifted up by wind is basically what we're talking about. And without boring you in the details, which are characterized in a paper we published this year in Environmental Science and Technology, we see interesting differences where, for example, in Colorado, in the central part of the US, in the Rocky Mountains, about 55% or so of the dust is actually derived from Asia, in particular in relatively wet winter and spring seasons. But in the dry seasons, somewhat, maximum 37%, but it could even be zero at different seasons, is derived from Asian source. But Asian source seem to be the dominant sources of dust. In California, we investigated dust collected from high and low elevation across the Sierra Nevada as a very a very steep high elevation system. So when you are in the low elevation system, about 400 or so meters above sea level, there's somewhere between 14 to 22% of the dust is derived from Asia. But in high elevation systems, in particular in drier systems of late summer and fall, 12 to 38% of this dust is sourced from Asia. What this says is that in California, California, a relatively drier system that's also, agricultural region of the country, there's a relatively large proportion of, in particular, local dust derived from the Central Valley of California, especially at low elevation systems. But at high elevation, you have more Asian-derived dust. Okay, and we were again able to apply XANES to speciate the dust samples that we collected across many of these ecosystems, and done that repeatedly with the different types of approaches to verify what we're looking at, because this is kind of one of the very few times that this kind of work has been done. And we find is like very surprising results that we didn't expect, that the dust brought with it a lot of organic phosphorus, that could potentially provide plant available phosphorus when it's deposited in soil. And this is important. Remember, this is why dust is outpacing the soil weathering and rock input that I mentioned earlier, because the dust derived phosphorus, in particular the dust that is in higher elevation systems, seems considerably more enriched in organic species that are more available and that are likely to make huge significant differences for the soil productivity and the plant productivity in the short term. Long story that I told you in a lot of details, but the bottom line is that I hope I have convinced you that using XANES along with traditional soil science and geochemistry approaches has been really beneficial in transforming work in the field of phosphorus biogeochemistry, and we are now able to get more accurate representation of what exactly is the phosphorus that's extracted with the different sequential fractionation schemes, and get an accurate representation of the different pools of phosphorus in soil and dust, and how phosphorus nature and speciation evolves with soil weathering over time. And we're also now able to see that dust inputs are significant sources of plant available nutrients, in particular in kind of temperate ecosystems that we studied. But we've also seen interesting differences in the source of the dust seasonally, where, remember, as I mentioned, in lower elevation systems in California, in particular at dry seasons, the big bulk of the input is coming from local sources, but in high elevation systems, in particular in wetter seasons, it's mostly Asian derived long range transported dust that's arriving in these ecosystems. And we've also seen the interesting and unexpected result that organic phosphate species dominate dust or particulate matter samples collected both at Florida and Colorado and California. And I think with that, I'll end. I'll just say that this work would not be possible without the generous support, both the financial resources as well as access to the instrumentation we received, again, from the Canadian Light Source, SLAC at Stanford, and the Environmental Molecular Science Lab at the Pacific Northwest National Lab in the state of Washington, and of course, many collaborators. Thank you.
Okay, thank you very much. I don't know if we have any questions. I didn't see any in the chat, but okay, I see there is one question from Masood. So it says, using XANES was a good idea for tracing. Do you think XAFs for the structural behavior around P atom? Did you think
there's some colleagues that are trying these approaches. So one thing I should have said probably is the fact that what makes using soil as a media for this kind of work very, very challenging is because soil has a mixture of, say, for example, if you focus on phosphorus, derived from many different sources over different time periods, and the concentrations are relatively not high. So any kind of adoption of these techniques has to go through a very protracted time period of trying to get these techniques to work with soil. So there's relatively few published works out there with XAF, only because they're still in development stages, but the possibility seems to be real.
Additional questions in the chat. And in the interest of time, I will just move on to the next talk, but I think you can interact with the questions in the chat. Yeah.
I will stop sharing my screen and I will respond to the chat questions. Thank you.
Okay, thank you. Our next speaker is Professor Tabitha Dobbins from the University of, from Rowan University. And this session, there are actually going to be actually four presenters. And you see they'll be going back and forth. And this is about the African Light Source Conceptual Design Report. So Tabitha did her bachelor's in physics from Lincoln University in Pennsylvania. And she did her master's degree in material science, also in Pennsylvania. And she did her PhD at Penn State. And she's currently professor of physics and astronomy at Rowan University, and also vice president of research at Rowan University. So Tabitha.
All right. Thank you very much, Dr. Foje, for introducing us and for the time to talk about the African Light Source Conceptual Design Report. And I want to introduce my co-presenter, Dr. Dorian Bowler, as well as Dr. Christine Dervais will be presenting later on in this talk, and Dr. Riccardo Bortolini for his useful inputs to this talk. We see the Conceptual Design Report of the African Light Source as a sort of a starting point to begin to discuss with ministers of science, with presidents, with leaderships in the continent of Africa about this project, so that they can really have a good concept of whether they can position it in their country. And so we really think that this is a very integral part of the entire process. And I would like to walk you through a few steps of what we have done so far in getting to a conceptual design report. So I don't have to tell anyone on this call that we are really working on a significant project in terms of cost of about $1 billion. And as you know, the major question we get as we go and present and inform people, scientists and others about this project, is they immediately want to know where in Africa. And we always give the response that we don't have a location, but instead we are working towards a vision, so that some country will decide to position it there in their home country. And we see this as a coalition effort. These light sources are quite expensive, and so we see it as a coalition of countries. The other thing I want to emphasize with this image, this True Size of Africa image, is that the distances are not represented on our typical global maps that a researcher would have to travel even within the continent of Africa to reach to the light source. So you can see the true scale shows you that even one light source is going to still have quite a significant travel distance to reach that light source. So we speculate that within 20 years we will have this light source, and the how it will occur, and from 20 years, not from now, but from where we began the concerted effort, which I would say was earlier than maybe 2014, earlier than that. A little bit earlier than that. It's hard to pinpoint. Finally, the how deals with what we lay out within this conceptual design report, and that's why we see this activity as so significant. Now, the one thing that will be different about the African Light Source Conceptual Design Report is that we are putting more emphasis into describing the socioeconomic benefits than you would see as a conceptual design report out of say an upgrade to the advanced photon source, or an upgrade to any of the other light sources around the globe. And the reason that we want to position this here is because we see this, the African Light Source, as a major contributor to boosting scientific research, boosting capacity building, preventing the brain drain, as you heard in earlier presentation by Dr. Diallo. This is very important, a very important tool to be positioned on the African continent, and we want our conceptual design report to effectively communicate that. I'll let you read for yourself the other reasons, and I want to say that we also view and within the scope of the conceptual design report, as you'll see later, we view the importance of the technical infrastructure, the additional facilities, industries, and companies that will accompany this light source, companies that will support technology solutions, but also companies that will support just the visit and the hotel and restaurant industry around this light source. So there will be a section commenting on and discussing those types of options. And we've seen this happen in Brazil near the Brazilian light source. We've also seen this happen in New York, in Ithaca, New York, around the Cornell University light source called CHESS, and that this infrastructure of companies that are able to thrive because of the existence of those light sources. We can look at this slide, and I took this from the Department of Energy, Brookhaven National Lab. We can look at this as I use it as an inference. It's not an exact causal relationship, but we can see on the left, on our y-axis on the small diagram on the left, we're looking at the brightness and brilliance of the light source, how much intensity, how many photons per square millimeters per second are able to be generated by those light sources. And we can see over the years that those numbers have increased, and we've gone to more brilliant light sources of the third generation. We do anticipate our light source, as you'll hear in Dorian Bowler's presentation, we do anticipate our light source to be a fourth generation light source. But the inference I like to make is that's shown here is the side-by-side analogous increase in synchrotron publications coming out in high impact factor journals and other journals of synchrotron and free electron laser science. And what we see is that this, the inference here is that the intensity of the light is actually driving the science. In the next slide, I just want to show you another view, and this is number of science papers published. This is a worldmapper.org. It's a website that will allow you to choose any factors. You can choose number of Nobel Prizes in a given year. You can choose, in this case, I chose number of science papers published. You're limited to your choices. 2016, I think, was the last update. But what the software does is it then rearranges the globe so that the size of the country and continent, in this case, depends on the number of science papers published. And you can see that with the growth of a light source, if it indicates that we're going to grow in the number of publications, then it also indicates that that we will grow in our influence in something like a data metric, such as represented here on the world mapper. So about our CDR, just to give a historical perspective, we like to think that it started in November 2015 with the Grenoble resolutions at the first African Light Source workshop that was held at the ESRF. And I have an image of those resolutions there. You can also find this information on our website. In January 29, Dr. Ernie Molyneux presented a CDR white paper concept, and we ran with that concept from there, and knowing that we would have to pull together a committee and a more concerted effort. And so by November of 2019, we had our first meeting of the Conceptual Design Report team. It was approximately 10 members, and we proceeded with our work, and so now and we've also proceeded with the growth, and now today we have about 20 members, inclusive of 2 student members. They may be recent graduates, but they started with our committee as student members, and we're planning for a full CDR to be completed, hopefully by the November 2021 meeting in Kigali. So just to introduce to you who is serving on this, we have a wide range of people serving on it in terms of their career, where they are in their career. As I said, that we have students as well as we have more senior personnel. We have a diverse group in terms of geographic location serving on this committee. And we convene our meetings roughly once a month to continue to work towards this conceptual design report, inclusive of fundraising activities, and inclusive of, as you'll hear by the last slide, inclusive of efforts to bring additional voices in on the discussion as it makes sense. And so here you have the URL, the website where you can read about the conceptual design report a little bit more. And so next slide. So right now we have 4 volumes envisioned. We have a 5th volume in planning, but right now we have 4 volumes fleshed out in detail. The first volume will cover political, economic, development, and management concepts. The second volume you'll hear in detail by Dr. Bowler, machine design concepts. Then we go into what will be at the beamlines, and that's volume 3 with our scientific case and technical abilities. And then the volume 4 is our integrated site design and construction. We need to consider, we need to provide the governments that may be considering positioning source in their country, to provide them with some information about what would be necessary for the site. That's one of the earliest questions they will ask. Now, just to show you guys a breakout of the various volumes, the first volume has 6 chapters. You can read them there. The second volume then has 4 chapters. And again, this may grow in terms of the volume 3 having only 1 chapter. We may see that the need to break that out into more chapters. And then volume 4, the integrated site design, you can see that we have the details kind of in mind, inclusive of the computational infrastructure that might be needed at the time that this light source would be built. And we always have to remember that we are working on a time scale where what is going to be necessary computational wise in the future may not be what would be necessary today, and we're keeping that in mind as well. Now, to introduce to you guys Dr. Bowler, who will go through the volume 2, the what you see as a typical conceptual design report is the machine design. So I will pass to Dr. Bowler, and we'll change the slides as he suggests, or unless he would like to share slides.
No, you can continue to drive. And just a correction, it's just Mr. Bowler. I don't want
Okay, my apologies.
myself here, but I am very happy to speak to you today to just give a quick update on volume 2. I believe there's been quite a bit of activity. So over the past few months, we have been reviewing and building a catalog of design reports. We have a white paper that we're currently drafting that'll really kind of follow most of the key points of this talk. We've been recruiting others to join the effort. And, you know, this group, Christine, Ricardo, and myself, we're really committed to organizing and contributing to the drafting of the document. So I wanted to just mention, in order for us to move forward, there are a few things that we need in terms of feedback from the community and from the committee. And that's to establish the key parameters towards the light source that is actually designed. And so the first important key parameter is the brilliance, or brightness, so to speak, which is just a crucial indicator of the overall machine performance. It relates the number of photons produced, the angular divergence, the cross-sectional area of the X-ray beam, as well as the bandwidth. Another key metric is the emittance of the electron beam, which essentially characterizes the area occupied by the beam. And in each plane, it's simply the beam size times the divergence. And so the key point here is that higher brightness photon beams are generated by small emittance electron beams. And so the smaller the emittance, the higher the technological challenge. And so the more, the more difficult, it is to design your magnetics and your injection and stability systems, et cetera. And so we'd also like some feedback on the photon energy range, perhaps the number of beam lines, and even the total budget, which we'll get to. Could you go to the next slide?
Yes.
So many of these points have already been mentioned, but I wanted to go back to the socioeconomic case that Tabitha mentioned, just to underscore a couple points. And so it's first that when we talk about tackling diseases endemic to Africa, crystallography is no doubt one of the greatest tools that we could use to determine structures, especially, the structures that are medicinal targets that are being used worldwide. Now, if we compare the larger beam sizes at third generation sources to the now submicron beam sizes at the state-of-the-art or fourth generation light sources, the key point here is that the higher flux at the fourth generation sources give us greater efficiency and ability to determine structures. And that's going to go a long way towards providing Africa with the most powerful tools to fight some of its most infectious diseases. On the right, what I'm showing here, we've mentioned COVID a few times. There is a lot of research going on at light sources around the world that are developing drugs, engineering antibodies, and even studying the effectiveness of PPE. What you see at the top right is a tomographical image from the ESRF in France, which is a fourth generation source which provides outstanding soft tissue imaging. And on the bottom, you see brain tissue being imaged. And both of these are resolutions on the scale of 6 microns. Next slide, please. And then the second thing that I wanted to mention in reference to fourth generation light sources is the advances in spatial resolution. And so that's really going to push the envelope of each one of these areas. If we're talking about energy research or mineral extraction or even human origins, it's really going to drive what we can do with the machine. And so I give two examples. One, a 13-million-year-old fossil that was discovered in Kenya, but imaged at the ESRF. And the images were so high quality that we were able to determine many details about the brain cavity, the inner ears, the teeth, and the age of the fossil. And that gives us a lot more clues about the early connections between humans and primates, et cetera, which is really exciting for that community. And I think these studies should be able to be done in Africa. On the right, I'm showing an image of the Swiss light source. And this, an image generated at the Swiss light source that's showing a fully imaged chip down to the 10 nanometer scale. And the technique that was used here is actually the only non-destructive method to image integrated circuits. And as you see in the literature, this has many applications in both security and failure analysis. Next slide, please. So now that we talked about, state-of-the-art machines, I thought that it'd be useful to just show you a survey of about 30 synchrotron light sources worldwide. And in this plot, you're looking at the emittance, which is normalized by the beam energy on the left scale, and then the circumference on the right. And the essential relation here is that emittance scales with the number of dipoles in the lattice. So the key trend here is that facilities that focus on or that employ double band Achromat technology are now trending in a factor of about 100 reduction in emittance to the red line, which is based on multi-band Achromat technology. And there's even a further reduction in emittance at facilities that are employing technologies like on-axis injection. So I want to give two examples here. In terms of an existence proof, is Max 4, which you see directly in this center of the circle that I've drawn, as well. And Max 4 was actually built from scratch. The other example is like the ESRF, which I've mentioned a couple of times before. And I just want to mention that these are real facilities that are operating right now. And these aren't paper designs. They've already solved many of the technological challenges. So my takeaway is that, Africa is essentially ready to build a fourth generation light source at the state of the art that would operate and improve over the next 20 years. This graph also shows that facilities don't typically end up where they start. And so what I mean by that is, the ESRF on the blue line, you see that there's a ESRF2. You see diamond on the blue line, diamond 2. And so these facilities are expected to, operate and receive upgrades. And in my opinion, I think you see a hot spot that I've drawn here in the middle of the plot that would indicate a machine about 500 meters in circumference at around 3 GeV energy would actually be a great tool to support world-class research in Africa. Next slide, please. So I hesitantly talk about cost because there's a lot of study that actually needs to go in, but I think it's very important to mention that all I'm trying to convey on this slide is the relative magnitudes of the projects. There are many assumptions. And so in each one of these cases, we are not comparing apples to apples. But to use MAX 4 at a cost of $750 million, as an example, approximately maybe 250 million of that is beam lines. There is another big portion of the cost to develop and build 20 or so buildings on site. And then there's another chunk of that goes towards the 14 out of the 21 beam lines that will be constructed. Now, if we look at the bottom of the box on the left, you'll see diamond at a much lesser cost. And the main driver there is that diamond is able to use existing infrastructure. So they didn't have the same cost in developing the site. Just above it is I'm showing about 300 million for a light source in Thailand, the second there. And they budget about 60 million towards the accelerator, 30 million towards the storage ring, 30 million for beam lines, and so on. So I just wanted to give some sort of flavor for the scale that these projects can have. A quick point that I want to stop and earmark is I don't really think the risk on developing a facility like this is on the design. There are mature tools that are being used worldwide that make these facilities really successful upon construction. So we have particle tracking codes, where we can optimize the beam lattices, and there's 3D mechanical design software, and there's an international community of experts. And it's a really collaborative nature once you look at how many of the labs have been developed and constructed. The opportunity that I see for Africa is actually one of expanding its industrial capacity to support the R&D. And so that's where, you could throw any number out, but I just say, it could easily be a $250 million investment to do things like, develop facilities that would support high standard machining. And so when I talk about that, I mean, computer numerical controlled machining, CNC, that allows you to machine to, micron precision, which is required, vacuum, vessels and magnets and things like that. But I think that the opportunity is so great because there is going to be a vast expansion and, expertise in many fields. This is going to lead, as Tabitha mentioned, to an extreme improvement in terms of local infrastructure. So if we talk about power, computing, travel, and many of the other, corollary things that are associated with a light source like this. But most importantly, I see it as a true opportunity to usher in the next technological workforce in Africa. So the technicians, scientists, and engineers, will all have the opportunity to be trained. The key part of the CDR is to make sure that all of these opportunities, that there's a strategy to actually realize the opportunity so that there's a true transfer of, resources and expertise to African citizens. Next slide. So I'm just going to briefly mention a few of the components related to synchrotrons. So there are many variations on design, and so this schematic is simply showing that, you know, there's the source is typically an electron gun, and the electron bunches are accelerated in a linear accelerator into a booster ring, where the electrons are accelerated up to the same, typically accelerated up to the same energy as the storage ring. Now, once in the storage ring, the beam is maintained on a closed path by the bin achromats. And as you see, there are different bin achromat technologies which determine the overall performance of the machine. And then there are also insertion devices like, you know, wigglers and undulators, which are the means where the highest brightness X-rays are sent to the experimental hutches for experiments. Next. So I'll stop quickly here just to talk about injection technologies. I'm showing an old rendering of Max 4 on the left. And I just wanted to point out that several light sources worldwide plan to use a LINAC as a basis for future free electron lasers. So this is a LINAC that's fully capable of supporting a free electron laser, just to distinguish from the previous slide. And FELs are interesting because they actually offer a peak brightness of about 1 million times higher than the 4th generation light sources. And so having a clear path to the next upgrade built, you know, from day one on a particular project is a very, it's happening at a lot of other facilities worldwide. I'll just say that. Now, the drawback or the reason you wouldn't start with the FEL is because its lack of capacity to support users. It's brighter, but LCLS, where I work, we can only serve 1 or 2 user groups at one time. So I think it really makes sense that, you know, we keep the conversation on synchrotrons. On the right, what I'm showing is a photo of a schematic of the Swiss light source. And what I want to point out here is that you see the booster ring is actually in the same tunnel as the storage ring. And so this, the way this operates in many light sources follow this design practice. It's called top-up mode, and that's where the booster ring accelerates the electrons to the same energy as the storage ring, and then it's, you know, the energy that's lost is just topped up, so to speak, in small injections. There is another novel technique that's termed on-axis injection, and that has the benefit that you provide even smaller betatron oscillations. And so the only takeaway there is you get even improved emittance, if you remember the original plot I showed. Thanks. Next. So I won't be able to give a lot of detail here, but I just want to underscore there is a lot of expertise worldwide that could contribute to the design of a 4th generation light source. And so one of the key considerations in a CDR, or one of the starting points, is to determine what your complement of, you know, bin magnets, quadrupoles, and sextupoles, your bend achromat, so to speak, how that's going to impact the overall electron beam profile, which is ultimately going to determine the emittance. And so those are one of the, you know, first calculations or analysis that would need to be done. Overall, I'd say that the magnet technology is extremely just crucial, really because of the tight tolerances that are required for all of the, you know, high precision devices on the beam line. Next slide. So the story, or the takeaway here, is to achieve the high brightness that we're talking about. And as you see, the diffraction limited storage rings are the 4th generation light sources I've been referring to. So to achieve the high brightness within an adequate photon energy range, which we need to determine what that energy range is, we require a cleaner spectrum. And so what I'm showing here is just comparing the spectrum you see in a 3rd generation set of undulators versus 4th generation. You see a much cleaner spectrum, which is going to give you capability to improve imaging and experiments across the board. It's too many to name at this point, but in order to proceed, we need to determine and need to get some feedback on the photon energy range, the brilliance, the emittance, perhaps even the number of beam lines or target budget from the committee, because we're really ready to move forward. We are preparing a white paper, as I mentioned, that we'll publish pretty soon, which will give a few more details. Next. One more click. Christine, would you like me to, or would?
So I can, if you want, so finish on this slides. You want, or?
No, I'll let you go. I'll introduce
Christine.
Christine. Yeah.
Yeah, very good. So last but not least, so what's the future in terms of activities? So what we have gathered there in this last slide, so this is maybe not only for the CDR itself, so which was the topic of this presentation, but I think a bit beyond. So the next step, because everything is as well, as you have seen, to be proactive. So because it has been already over the years, quite a lot of plan and possibility as well to gather information to build on those best practice, I would say. So in the beginning of next year, so we have thought to start with some topical webinar. So there is some workshop that could look at the different aspects of the project. So this is one of the important parts, so to gather with different teams, so the different expert, and try to build up, so through some white papers, some possibility later on to combine everything in this CDR, which is essential in order to be able to show what this light source can do, and to look at over the time, over the 20 years, how everything will be done. So to be able to do that, of course, we will need to better understand and have a better survey of what exists. And this is why with the different light sources that exist around the world, so it will be very important to merge as well with their knowledge and their capacity, and to transfer those technology as well, just like their own knowledge. So to try to understand what already exists and to try to see what the African community really needs. So this is one of the important aspects. So we saw already from the previous scientific case that there's a lot of capacity that can be built from this light source and this research infrastructure implementation. So now to look at, after a better definition of what the scope would be, so this is to look at the cost and then the schedule. So this is why we need really to spend a bit more time, or to spend a lot of time, I would say, to better establish the different activities with this breakdown structure, so working breakdown structure, to define the different tasks, assign people, assign costs, and then from this we would really have a better credibility in terms as well of following up, so a process and being able to support the current roadmap that has been shown previously. And so one of the things that is very important as well, because we've seen that over the 20 years, so there will be the need of having a lot of different diversity of people. And one of the aspects of that is the training, the teaching. So for instance, so here the community to be trained will be, so the scientists, but as well the engineers and the politicians, certainly a lot of different aspects. So here I put a link for a MOOC, so this massive open online course. So with the modern technology now, we have really access to a lot of knowledge, and this NPAP, so Nordic Particle Accelerator project, has been run so since with a grant that has been received from the European so the European Commission, from the strategic partnership. So since 2015, based on some school, we have then developed this massive open online course, 3 of them mainly that could help to build up so the next and the African light source. So you have as well in the website of the African light source the link for this resource and the way to train so the coming scientists to use all of that. So how to define a light source, looking at the historical, and then build up from those knowledge to try to see what you need. So like Dorian was mentioning, so the different components, what they're used for, and how can we get the best possibility as well to have not a new, maybe state-of-the-art machine, but something that will be really effective and that we could build. And then the last MOOC so is more on the possibility for the medical application, and something that for the community could be also of interest. But teaching training is something which is really of main importance in all this prospect. So this is why we have as well with the African School of Fundamental Physics and Application, so also introduced by so Ketavi that gave a presentation earlier, and I've been as well part of the team and the main organizer since 2010. So we have a lot of effort with now an additional effort by having some online courses. So in addition to teaching to students, in addition to trying to have as well with so the forum, the possibility to communicate with policymakers, what would be the different aspects of a light source. And then I can mention there, and I've seen as well that we have also Professor Waynegate with the possibility to implement the idea of the need for this light source. So that's something that we have also developed during one of our forums, so in Senegal in 2014. So that was a really interesting as well milestone at that time. And then we have, so now, as mentioned, so teaching teacher, teaching student, and then mentoring the different students and alumni that we had, but to adapt each time from the topic. One of the important things is for this aspect of the light source, the possibility to learn more in terms of how to build those light sources. And then we have, so the next lecture series that will be so given by Professor Andrew Harrison, and that will be as well the possibility with 6 courses to understand more what the light source can be, and to have a full panel of different discussion as well that we will have at the end of the course. So, and then the important thing and the important aspect, as it was so underlined and with the previous presentation, and I completely resonate with that, with the possibility really to grow this ecosystem in an harmonious way. So by really looking at the training, like the possibility to have the actor of this light source in every discipline, but as well with the industry. So we need really to make sure that in Africa, the industry will be strong enough to be able to support all those different developments. And then to have, of course, so with this research infrastructure, then the possibility to drive and to get the local community involved. And this is this word, so the concept of Ubuntu, that I have to admit I really liked. I've discovered it in 2010, and this is really by, so because we are, so it can be that this light source can become a reality. So the future activity are also related in the possibility to be actor, and then having as well, so the possibility to contribute to this project, which I think is an important step forward. So that's the main message I think that we can take from that, if there are any questions, and then we will be more than happy to be like, and to engage the community. I think that, like Uncle Sam said, so we need you.
Would you introduce yourself, Christine? We missed your introduction. If you could say where you are. And
introduction, yeah, so in a nutshell, so I've been so working at CERN and at Fermilab, so over the last 20 years, so building different equipment for accelerator, but as well being on the side doing a lot of activities that are related to enhancing the different possibility to transfer knowledge, so through some different schools. So like, for instance, this Nordic Particle Accelerator School or the African School of Fundamental Physics and Application. And so working mainly on cold LINAC, and this is what is maybe not needed in Africa, but still we need to find ways to accelerate charged particles as well. So that's
thank you.
Okay, thank you. I think that was a really interesting presentation by our speakers there. So there are 1 or 2 questions I saw in the talk. There was, I think Nabil was asking about building materials, like sustainable building materials that are being developed in Morocco. So what, if anyone has thought about using those?
I will comment on that. At this point, so this is something that is very interesting to us. You notice in our volumes, volume 4 is the construction section. And at this point, we are just trying to accumulate volunteers who will be working on that section. And so we welcome any additional input, anyone else who would like to contribute. I hope this comment is in the chat so that we can hold it and have the information of the details that you just asked in the question.
Okay.
Likewise, I saw the question related to whether all African countries are already included in the project. As you saw, this is only one subcommittee, the Conceptual Design Report team. We doubled in size in this 1 year, and we have much more capacity as the first bullet point on the Christine slide showed that I will go back to that slide, that we will be holding a series of panels, and I think this virtual format has really helped us out a lot, that we can now start meeting under subtopical groups, even within the CDR. So we will be reaching out to the broad community to begin meetings. Our initial meeting will describe how these topical groups will work. We already have leaders for each of these topical groups, and you can think of the topical groups as maintaining one of the chapters that you saw earlier in the slides. And so we have leaders who will be convening, put out broad agency calls, and so broad calls, so you will be able to see where you can join a topical group. And our intention is to have every country represented within the project, and the interests of every country represented in the project.
Okay, so we have another question from Ian Swenson. Have other synchrotron projects shared project management plans, including timelines for planning?
Yeah, I can comment on that one, and then I believe Christine could probably give more context to WVS directly. But for the data that I actually showed, I used the International Particle Accelerator Conference survey. So every year they have a publication where they give an overview of all of the active projects in particle and accelerator physics, and it actually includes, you know, high-level budgets, timelines, contacts to project leaders with emails. And so I would envision that one of our next steps on this piece will be to reach out to those directly.
Exactly. So this is exactly the step, to use what we already know and to try to have the order of magnitude that would be in compliance as well with the needs that might be a bit different in Africa. So certainly looking at the contingency, maybe it will be different, because in the context of Africa, there is a lot of industry maybe that are missing, or dynamism that would not be the same. But we will definitively have to look and study all those different cases first.
Okay, thank you very much. I think the fact that a lot of people are still here, even though we went a little bit over, just demonstrates how interesting the talks were. And please join me in thanking the speakers for the session. And this was the last session for today. I should just remind everyone that there is a poster session on Friday, but take some time after this to visit the links and inspect the poster abstracts. And so thank you for joining us today. And for this one moment, if you can unmute your mics and give a hand to all the speakers.
Thank you very much.
Thank you very much for
Acknowledge if you've enjoyed today's portion of the workshop, I would like to acknowledge the International Conference Organizing Committee, who were responsible for this, and thank you all for staying until the end. The posters you'll find instructions on how to reach the posters in the Friday session. You can click on it and get the details and subsequently download the posters that are available there. We're expecting more posters. Bye-bye, everyone. Have a good day.
Bye.
Okay.
Bye-bye. Have a good day. Bye, Sekazi.
Bye. Bye. Take care.
Bye.
Tabitha, bye.
Bye-bye.
Bye, Sakazi.
Bye-bye.
Take care.
Bye. Bye-bye.
Bye-bye.
We'll see you all tomorrow morning.
Yeah, see you tomorrow. Yeah.
Yeah, see you tomorrow morning. Bye-bye.
See you tomorrow morning.
See
Bye-bye.
you. Bye.